Hello everyone, welcome back to the module Advanced Heat and Momentum Transfer. And for this video, we will be covering the second lecture on Introduction to Molecular Momentum Transfer. So before we begin with lecture 2, let us recap back on some things that you have learned in previous week. So in the first lecture, you are introduced to the three different types of transport phenomena where we have the momentum transfer, the heat transfer, and mass transfer. So I hope that you still remember the drawing force that underlies these different kinds of transport phenomena, where for momentum transfer, it will be due to the velocity gradient, heat transfer is due to the temperature gradient, and mass transfer due to the concentration gradient in most cases. So besides that, we also talked about the transport mechanism in lecture 1, where you have two types, the molecular, a diffusion transport, and the convective transport. So then you are also introduced to some constitution law, and we review back on some of the conservation law. And towards the end of the lecture, you are introduced to some of the mathematical operators, the equations. So that's what we have covered in lecture 1. So before we begin with lecture 2, so let's look at this figure here, where this is a picture of a chemical plant. Alright, so now what I would like you to look at is, you can look at all this, we have different pipings here. So the pipings, they come in different size and different lengths, and then we have different unit operation. So in a chemical plant, there are various mass transfer, heat transfer, and momentum transfer processes that are happening in a chemical plant. For example, let's say if we have a chemical reactor, an exothermic continuous stirred tank reactor in a chemical plant, so we can actually observe three different types of transport phenomena in it: the momentum transfer, heat transfer, and mass transfer. Because one of it is due to we have flow of material into and out of the reactor. And then we also have the mixing of reacting medium, as well as the movement of the cooling media into and out of the reactor. So these will, therefore we will observe momentum transfer in the CSTR. So obviously also because there's the heat generated from the reaction is being transferred to the cooling medium, so it will also involve heat transfer. And because it's a chemical reaction, so it will involve the mass transfer phenomena as well. And another example that we can see here is the heat exchanger. So we understand very well that the heat exchanger, right, it's used for heating, or it could be used for cooling, where two different fluids, they flow past each other without contact, so that the heat can be transferred from the higher temperature region to the lower temperature region. So that's the heat transfer phenomena. So at the same time, because we have the fluid flowing in and out of the pipe, so it involves flows of fluids at different velocity as well. So therefore, due to the movement of the heating and cooling medium into and out of the heat exchanger, so momentum transfer can be observed, and it also occurs in the heat exchanger. So with the examples given just now, so hope you could better understand how the momentum transfer knowledge that you learned could be applied in the design of chemical plant in future. So now looking at the course outline, the content that we are going to cover in this module. So we have completed the introduction to advanced transport processes. So for this lecture 2, we'll be covering the first part of the second topic, the molecular momentum transfer. So for this topic, we'll have 2 lectures to cover it. And for this topic here, it's mapped to 2 learning outcomes, which is the first one, analyze the thermal and flow behavior of engineering system using the laws of conservation. And the third one, to formulate the temperature and velocity profiles for fluid flow on various surface geometry. So for lecture 2, we'll be able to cover this one, and the third learning outcome will cover it on the coming lectures. All right, the second part of this topic, molecular momentum transfer, next week. So for this lecture 2, so these are the subtopics that we'll be covering in this video. So it includes the introduction to molecular momentum transport, the viscosity of the fluid, what is Newtonian fluid and what is non-Newtonian fluid, and we'll look at some of the dimensionless number, for example, the Reynolds number, the Prandtl number, Nusselt number, and Biot number. And lastly, we'll look at the shear stress of power law fluids flowing in pipe. So, and for this subtopic, we'll work on 2 examples as well. So let's now look at the first subtopic, Introduction to Molecular Momentum Transport. So now, momentum transport happens because there is flow of fluid, and these fluid, remember, it could be liquid or it could be gas. So, and the flow of liquid, it could happen in like what we see in the figure earlier. It could be in pipelines, it could be in unit operations, the equipments. So, and fluid flow it can happen at different geometry. So for example, here, let's say we have gas pipelines, so it would then flows in cylindrical pipes. And here you can see liquid flows in cylindrical pipes in the chemical plant. So this would be the more common type of geometry. Besides that, we also have other geometries like the flows of maybe exhaust gas in square ducts. So in the coming few lectures, you are going to see how we are going to derive equations to solve for flow of fluid on different geometries. Now, let us look at some units related to momentum. So, what is momentum? Momentum is the product of mass and velocity. Well, for momentum flux, so it's the rate of momentum transfer per unit area. So in that case then, for momentum, the unit would be the mass, since it's kilogram, velocity is meter per second. So for momentum, it has the unit of kilogram meter per second. And when we are looking at the rate of momentum transfer, so you can see here, which is the momentum, the unit of the momentum divided by time. As for momentum flux, so it's the momentum rate divided by area. So it's kilogram meter per second and divided by second. This is the momentum rate, and divide by the area. And if we rearrange this, so it will give us kilogram meter per second square. And if you look at it, this is the unit for force. So which means the momentum flux is actually equals to force divided by area. Force divided by area, and it will give us the this unit here, which is Pascal. So momentum flux, we can say that it's also equals to force per unit area, and it has the unit of pressure, and it's also related to the stress. So in previous lecture, you learned that momentum flux is a tensor, and it can be grouped into 2 types, which is the normal stress and the shear stress. So all of these, the normal stress and shear stress, is force per unit area, and they therefore has the unit of Pascal for momentum flux. Now let us observe how the water flows through the pipes of different geometry. So in figure A here, we have a cylindrical pipe, while in figure B, we have an annular pipe. So let's say if we look at figure A here, and we take a cross-section of a cylindrical pipe and observe what's the velocity profile of the fluid that flows in it. So if we look at this velocity profile, it has a parabolic shape. And if we are looking at the coordinates, so towards the horizontal direction here to the right hand side is actually the Z direction. So if we recall back for cylindrical coordinates, we have three components, which is the radial direction, the z, and the theta. So these would be the z direction, and this is where we can observe the magnitude of the velocity. As for this one, this is in the radial direction. So then you're given here the radius of the pipe is equals to r2. So when we say velocity profile, the velocity profile actually shows us the magnitude of the velocity graphically. And at the same time, it also shows us the characteristic of the flow. For example, here, the direction of the flow. And the velocity profile will actually change according to the shape of the geometry of the shape of the geometry of the pipe, for example. So now for this, if you look at here, the velocity profile has a parabolic shape where at the center of the pipe, the velocity of the fluid will be traveling at the maximum velocity. That is when the r at the point r equals to 0. So the velocity is the velocity in the z direction, vz, it will be equals to v max, the maximum velocity. But as we look at here, the velocity the velocity actually decreases as it approaches the pipe wall, right? The velocity actually decreases as it approaches the pipe wall, and this is because of the no slip condition. So it means here that the no slip condition at r equals to r2 at this point, which is at the pipe wall. When r equals to r2, the velocity of the fluid at the stationary wall or the duct flow, it will be equals to 0. So which means at r equals to r2 at this point, the Vz would be equals to 0 because of no slip condition. Now, this is because the particle of the fluid close to the surface, it did not move along with the flow. It could be because the force of attraction between the fluid particles and the solid particles of this wall here is greater than the interaction between the fluid particles, which means in other words, we can say that the adhesive forces is greater than the coercive forces between the water molecule. So just to repeat, so in this velocity profile here, when fluid is flowing, so the boundary wall is actually static, the fluid is flowing inside the cylindrical pipe, so there will be a velocity profile built up. And at r equals to 0, the Vz would be equals to Vmax, is traveling at the maximum velocity. But the velocity will decrease as it approaches the wall. So, and at this boundary wall here, when r is equals to r2, the Vz would be equals to 0 because of the no slip condition. So we can see there's a velocity gradient within the fluid. Okay, so it will be the same on the other side as well, it's symmetry. And then if we move on and we look at this figure B here, so we have an annular pipe, or you can imagine it as a larger outer pipe with a smaller inner pipe, like what you would see in the heat exchanger, right? The heat exchanger, the double pipe heat exchanger when you study the thermodynamic and heat transfer. So let's say our focus would be the flow of the fluid in the annular space. All right. So the inner pipe, it has a radius R1, capital letter R1, while the outer pipe, right, it has the the radius of R2. So let us look at the annular flow, the velocity profile of the annular flow, which is flowing between the inner pipe and the outer pipe here, which is the annular space. So the velocity profile is, it also has a parabolic shape, because at somewhere near the center here, the velocity of the fluid would be at the maximum Vmax. But as the layer of fluid which is closer to the pipe wall, either the outer pipe or the inner pipe at these two ends here, you can see, so the velocity of the fluid which is just adjacent or in close contact with the pipe wall, the wall boundary, it will be equals to 0 because of the no-slip condition. So these are the example of the velocity profile for the laminar flow in cylindrical pipe and also in the annular pipe. Next, let us look at this diagram again so that you can better reinforce your understanding about the momentum flux. So now, in this figure, we have a pair of large parallel plates, and each, let's say, with an area of A, and these plates, they are separated by a distance y. So at time smaller than 0, initially, the fluid which is sandwiched between these two plates is still at rest. The fluid, it could be gas, it could be liquid. So then, at time equals to 0, let's say we set the bottom plates here in motion. So we set it in motion in the positive x direction. So this horizontal line here, positive x direction towards the right hand side, and at a constant velocity v, capital letter V. So then as time proceeds, at a very, very small time period, let's say a few nano or microsecond, there will be velocity built up, but it would still be an unsteady flow. So you'll see the velocity of the fluid layer, which is just at close contact with the bottom plate, which is set in motion, it will have a velocity equals to this capital letter V, but the fluid layers that is adjacent to it, right, as the fluid layers approaches another side of this wall here, so you can see that velocity is decreasing. And at this moment, the velocity of the fluid in the x direction is a function of the distance, from the lower plate, and also a function of time as well, because it's an unsteady flow. So as time proceeds further, at a very, very large time t, eventually, steady flow will establish, and then we'll obtain this velocity profile for laminar flow. So now for the velocity of the fluid in the x direction is only a function of the distance from the lower plates, because you can see here the same thing, the fluid which is the layer of fluid which is at close contact with the surface of the bottom plate, it will travels at the same velocity of the bottom plate. But the fluid which is just above it, and then the following fields, the velocity decreases as it approaches the top plate, where at this point, when y is equals to the, so when the distance y is equals to the large y here, the Vx would be equals to 0 because of the no-slip condition. So then, from the previous slide, you learned that the momentum flux is actually equals to force per unit area, and is equals to, it can be expressed as the shear stress. So, and the force that is applied to maintain the flow of the fluid at a constant velocity v is proportional to the area, the velocity, but inversely proportional to the distance. So if we rewrite the v divided by y in terms of the derivative, so it would be the change in the velocity of the fluid divided by the change in the distance between the plates. So now if we want to rewrite the equation which is represent this case here, so it will be the shear stress, right, which is the force which is in the x direction on a unit area which is perpendicular to the y direction. So it's an x-directed momentum in the positive y direction. So it's equals to the negative mu dvx dy. Let us look into further detail of the velocity profile for the fluid that is flowing between two parallel plates, which in this case here where the lower plate is set in motion. So we have the coordinate x and y here. So the two large parallel plates, they are separated by a distance y, and let's say it's equals to y4, and you have each layer of fluids at a position y1, y2, and y3, and y4. So at steady state, there will be a force that is applied on these lower plates here to maintain it in motion at a constant velocity v. And the momentum will be transferred from each layer of fluid such that each layer of fluid will move in the x direction. So what happened is the layer of fluid, these layer of fluid which is in close contact with the lower plate, it will be carried along with the lower plate at a velocity v. So which means for the velocity of this layer here, the vx1, it will be equals to the velocity of the plate, v plate. Then the layer which is just above it, it will travel at a velocity which is slightly lower than the lower layer, which is in close contact with the moving plates. And the same goes with other layer. Each layer, they will move at a slower velocity as it approaches to the top plate here in the y direction. So you can see at position y equals to y4 eventually, the velocity of this layer of fluid which is in close contact with the static top plate, vx4 would be equals to 0 at y equals to y4, which is the no-slip condition. So which means there exists a velocity gradient on the fluid in the y direction, where so you'll see that the velocity vx1 at y equals to 1 is equals to the velocity of the plate, and it will be larger than vx2, and vx2 will be larger than vx3, and this would be larger than vx4, which the vx4 would be equals to 0. So in summary, the momentum flux is similar as shear stress. So it's force per unit area. So for the case that we are analyzing just now, you can see the velocity profile. This is the velocity profile if it's fluid flowing, right, in one plate that is the lower plate that is moving while the top plate is static. And earlier you have looked at the fluid flow, the velocity profile for fluid flow in cylindrical and annular pipe. So now for this case then, is the force is acting in the x direction on a unit area which is perpendicular to the y direction. So that's why it's expressed in this form here as the tau yx. This is the shear stress. So we are using this tau symbol here. If it's normal stress, then it's the sigma symbol. So this is defined as the force in the x direction acted on a unit area which is perpendicular to the y direction, and it's equals to the negative of this mu here is the viscosity, which is the resistance to flow, and the first derivative of vx respect to y. So this would be the driving force, the velocity change. Next, we'll look at the second section of this lecture 2, which is about the viscosity of fluid. So now, liquids have different viscosity, and the viscosity is actually a properties of the fluid. So if you look back at this equation here, so you can see that shear stress is equals to negative of the viscosity multiplied to the first derivative of v respect to the y, the distance. So this viscosity is resistant to flow, is a fluid properties. And if you look at this diagram here, so we have different kind of fluids. So you can see the last tube, we have the last two tubes here, we have very, very thick fluid that has very high resistance to flow. So these we can call it as fluid with very high viscosity. As compared to this, you can see here we have a streamlined flow here where the fluid can flow very smoothly, so it has a lower viscosity. And for fluid, it can be categorized into two types, which are the Newtonian fluids and the non-Newtonian fluids. For Newtonian fluids, you can see that the shear stress is proportional to the velocity gradient. But for non-Newtonian fluids, the shear stress is not proportional to the velocity gradient. Now, let us talk about the viscosity of liquids. So, if the viscosity is expressed in terms of density, then we can call it as the kinematic viscosity. And this kinematic viscosity, if you look at it, so it's actually the viscosity divided by the density, and it has the unit of meter square per second, or the stoke. So 1 stoke is equals to 1 centimeter square per second, or in SI unit, then it will be 0.0001 meter square per second. So the viscosity of a fluid is a measure of its resistance to deformation, or you can say the resistance of the fluid to flow. So it's because it acts like friction between layers of fluid when they are forced to move relative to each other. So there's friction between layers that restrict the movement of the fluid is because for example, in liquid, there would be intermolecular forces between the liquid molecules. So, therefore, if you like to decrease the viscosity of a fluid so that it can flow smoothly. So, what we can do is we can heat up the liquid, because with the increase in temperature, so some of the intermolecular forces can be broken. Some of the intermolecular forces between the liquid molecules can be broken, and therefore the increase in temperature could decrease the viscosity of the liquid. Unlike liquid, where the resistance to flow could be due to the intermolecular forces between the liquid molecules, for gases, the resistance to flow in gas is actually due to the presence of random molecular collisions. So why does this would happen? So you just imagine a system full of gas molecules. So usually gas molecules, they are widely spaced from each other, which means the intermolecular forces between the gas molecules are negligible. So when the temperature increases, which means then the gas molecules will gain more energy, where it can travel more freely and they will collide. There would be higher probability of the gas molecule colliding with each other, and which means then with more collision, the gas molecules will transfer momentum from one to another more often. And with this transfer of momentum, the increase in momentum transfer, it will reduce the momentum gradient, which is the drying force, which is necessary for flow. So that's why with the increase in temperature, the viscosity of gas actually increases. They are more resistant for the gas to flow freely. So one can determine the viscosity of the fluid by estimating the slope of the graph, where the graph, which is the plot of the shear stress as a function of the shear rate, or we call it here the strain rate, or the velocity gradient. So a plot of this, right, the shear stress as a function of the shear rate, where you obtain a slope, and that slope, it will give us the value for the viscosity of the fluid. So besides obtaining the viscosity data from the plot of shear stress as a function of shear rate, so in this lecture slides here, I've also included some tables for the reference of what are the viscosity for some of the fluid. So for example, you find table 1.12 for viscosity data of water and air at 1 atmospheric pressure. And then we also have table 1.13 for viscosity of gases and liquids at atmospheric pressure, and table 1.14 for viscosity of some liquid metals. So let's look at some of these table here. So table 1.12, so for viscosity of water and air at 1 atmospheric pressure. So the data given it includes the viscosity and the kinematic viscosity. So kinematic viscosity, which is the viscosity divided by density. So take note of the unit also. Viscosity is in millipascal second, as for kinematic viscosity is centimeter square per second. So if you look at the data for the viscosity of water and air at 1 atmospheric pressure, as the temperature increases, you'll see that for water, the viscosity decreases because the intermolecular forces between the liquid molecules is broken down. But oppositely, for air, if you look at the data, so you find that the viscosity of air actually increases with temperature because of more collision, more molecular, the momentum transfer, and therefore it reduces the gradient, the momentum gradient, which is the drying force for flow. Then next we have here table 1.13 for viscosity for some of the gases and some of the liquid at atmospheric pressure. So these are tabulated at some given temperature. And then we have table 1.14 for viscosity of some of the liquid metals like lithium, sodium, potassium. So if you look at here for liquid metals, it has to be at a very high temperature here for this field, alright, in order for it to exist at a state that can flow. And the last one here for gases at non-standard condition. So the pressure and the temperature dependence of viscosity of a gas, it can be estimated using this figure 1.31, where in this plot it actually gives us a global view of the pressure, so you can see here the pressure, it gives us the global view of pressure and temperature dependence of viscosity for gases at non-standard condition. So these are non-standard condition because it's not at the 1 atmospheric pressure. So if you see here, this is the reduced viscosity, the reduced pressure, and the reduced temperature. So all this reduced quantity is actually a dimensionless quantity, which if you look at it, for example, reduced viscosity is the viscosity divided by the viscosity at the critical point. So the reduced quantity like the reduced viscosity, reduced pressure, and reduced temperature, this reduced quantity is those that has been made dimensionless by dividing these, like for example the temperature and viscosity and the pressure, by its corresponding quantity at the critical point. Next, let us talk about the Newtonian fluids. So if we look at this figure here, so let's assume that we have two parallel plates, two infinite parallel plates. Infinite, which means in this case it could be very long and very wide. And then suppose that, let's say if the bottom plate here is moving parallel to the top plate and at a constant velocity u. So it's moving in the positive x direction, and because there's a steady force F Newton here applied on this bottom plate. So then here the plates are y equals to h apart. So instead of earlier, it's denoted as the big Y in this one. So the distance between the two plates is equals to h. And as a steady force F is applied on the bottom plates here in the x direction, each layer of the liquid will move in the x direction as well. The layer which is immediately next to the bottom plate, it will be carried along the plate at the velocity of this plate, which means you can see here at y equals to 0, the velocity at this layer would be equals to the capital U, which is the same as the velocity of the plate. But the layer which is just above, it will be at a slightly lower velocity. And each layer, it will be moving at a slower velocity as we go up in the y direction. So you can see here the velocity profile is linear in the y direction as shown in this figure here. It has been found experimentally for many fluids that the force in Newton is directly proportional to the velocity, and it's also directly proportional to the area of the plate used, but it is inversely proportional to the distance between the plates for this case here. Or as given by the Newton law of viscosity, when the flow is laminar, then the force per unit area is equals to the negative of the viscosity multiplied to delta V divided by delta Y. So this mu here is the viscosity of the fluid, the property of a fluid. And let's say if the delta Y approach 0, so when the delta Y is almost equals to 0, then using the definition of derivative, so the force per unit area, which is also the shear stress, or also termed as the momentum flux, it's equals to the negative viscosity multiplied to the first derivative of the velocity with respect to y. So this equation here, this equation is called the Newton's law of viscosity. It's called the Newton's law of viscosity. And the Newton laws of viscosity here, from the equation, you can see that it states that the shear stress between the adjacent fluid layer is proportional to the negative value of the velocity gradient between the two layers. And if we rearrange it, so the viscosity can be expressed as negative shear stress divided by the velocity gradient. And also remember, the fluid that obey these Newton's law of viscosity, they are known as the Newtonian fluid. So you can see here for Newtonian fluid, the shear stress is proportional to the velocity gradient. So that's about the Newtonian fluids. Now we are going to look at the non-Newtonian fluids. So in the previous section, as we have looked at the equation, so if it's Newtonian fluid, it's those fluid that will follow the Newton law of viscosity, which is given by this relationship here, where the shear stress, right, is proportional to the velocity gradient, or this is also known as the shear rate. So if you are writing this in equation form, then it will be shear stress, right, yx with the subscript yx is equals to negative mu multiplied to the shear rate, which is the first derivative of Vx with respect to y. And the mu, which is a proportionality constant, is the viscosity. So if we are to plot the shear stress as a function of the shear rate, then it will give us this linear line here, right? So a plot of shear stress versus shear rate, which is negative dvx over dy, it will give us a linear line with a slope which is equals to, so the slope would be equals to mu which is the viscosity. Okay, then now let's look at this relationship. As for non-Newtonian fluid, it's those fluids that do not follow the Newton law of viscosity, or do not follow these linear relationship, where if we are going to plot the shear stress as a function of the shear rate, so you'll see here, when we plot shear stress as a function of shear rate, which is negative first derivative of Vx respect to y, it will give us lines which are not linear, passing through the origin. So example is the pseudoplastic fluids, the dilatant fluids, and another one which is the Bingham plastic fluids, although it's linear, but it does not pass through the origin. So now, if we look at here, right, for non-Newtonian fluids are those fluids where the shear stress is not proportional to the shear rate. So the non-Newtonian fluids, it can also divided into two broad categories on the basis of their shear stress and shear rate behavior, which is it's categorized as time independent or time dependent. So if it's those shear stress is independent of time, right, or the duration of shear, then it's categorized as time independent non-Newtonian fluids. Or if it's the shear stress that is dependent on time, or we say it's dependent on the duration of shear, then it's a time-dependent fluid. So what you can see here, the Bingham plastic fluid, the pseudoplastic fluid, and the dilatant fluids, these are the time-independent. So you can see here time-independent non-Newtonian fluids. So this table here summarizes some examples of the Newtonian fluids and the non-Newtonian fluids from the time-independent category. Now, let us examine each of these different types of fluids based on the shear stress and the shear rate plot. So if we look at Newtonian fluids, so we know that Newtonian fluids are those fluids in which the viscosity, right, it's linearly dependent on the shear rate, which is the first derivative of Vx respect to y for this example here, or it's also linearly dependent on the rate of applied force. So basically the viscosity of Newtonian fluid, it will only change if the temperature or the pressure of the surrounding environment changes. So some of the examples of Newtonian fluids you can see here, like we have air, the water, glycerin or glycerol, vegetable oil, and kerosene. Next, the Bingham plastic fluids. So these Bingham plastic fluids are very similar to Newtonian fluids if you look at the plot of its shear stress versus the shear rate, but it differs from the Newtonian fluid is that you can see that here the linear relationship, it does not go through the origin. Instead, for Bingham plastic fluid, for it to flow, there's a need to apply a finite stress. So this finite shear stress is known as the yield stress. So a yield stress is needed to be applied on Bingham plastic fluid to initiate the flow. And some of the examples of Bingham plastic fluid you can see here, which are the soap, the toothpaste, paper puff, sewage sludge, and chocolate mixture. If you imagine or relate it to toothpaste, right? So you have to apply some force on the toothpaste tube, so then only the toothpaste will flow out. So this is an example of the Bingham plastic fluid, where some yield stress, right, is needed to be applied in order to initiate the flow. Next, we have the pseudoplastic and the dilatant fluids. So here, pseudoplastic fluid and dilatant fluids, they are also known as the power law fluids. So it's given this name also is because if we look at the plot of shear stress versus the shear rate for both pseudoplastic and dilatant fluid, you can see that it's a curved. So now, when we talk about the power law, so it comes with the index, the n number. So for Newtonian fluid, it has n equals to 1, the index is equals to 1. For pseudoplastic fluid, the n is smaller than 1. And for dilatant fluid, the n is larger than 1. Now, so how do you differentiate between pseudoplastic and dilatant fluids? So let us talk about the pseudoplastic fluid first. Pseudoplastic fluids, or we also call it as the shear thinning fluids. So the viscosity of pseudoplastic fluid, you can look at this the slope of the curve. So initially it's quite high, right? And the slope is quite steep. But as the shear rate increases, you can see that the slope is no longer a very steep slope. So for pseudoplastic fluid, the viscosity of these fluid, it decreases as the shear rate increases. So and for pseudoplastic fluid, it's more common. We can majority of the non-Newtonian fluids are usually the pseudoplastic fluid. And some examples include the polymer solutions, starch suspension, the mayonnaise, biological fluids, or paints. And another example would be maybe quicksand. So now, if you just imagine, let's say if we relate it to the paint, right? When you open the can of paint, right, and then we will try to mix it. So initially, when you mix it at a slower rate, you'll find that it's more difficult for the paint to flow, right? But as we increases the rate of mixing, you see that the paint actually flows more smoothly, more easily. Or another example, right? Let's say the quicksand. So when someone walks slowly and carefully through the quicksand, it will still be fine, right? They will not sink. But as they run or they struggle and apply more force, so the viscosity of the quicksand will increase. Then it will hold that person in the quicksand. So these are some examples that you can relate to differentiate between pseudoplastic and dilatant fluids. So for pseudoplastic fluids, according to if it's for when we applied the power law, then you see that the index would be smaller than 1. As for dilatant fluids, they are also known as the shear thickening fluids, where if you look at the plot of shear stress versus the shear rate, so you can see that the viscosity actually increases with the increase in shear rate. And a very common example that you can relate to this is the mixture of cornstarch and water. Cornstarch and water, which it will hardens upon application of high enough forces. So some other example of dilatant fluids are like starch in water, potassium silicate in water, and some solution that contains high concentrations of powder in water. So dilatant fluids are far less common than pseudoplastic fluids. And for dilatant fluids, so their flow behavior, it will shows an increase in the viscosity with increasing shear rate. So the pseudoplastic and the dilatant fluids are also known as the power law fluids, right? So it can be represented by this power law equation. So take for example, if we are examining the shear stress of pseudoplastic or dilatant fluids at the wall of a tube, so then the power law fluids can be expressed, the power law relationship, it can be expressed in this form here, where the shear stress is equals to K, which is the consistency index, multiplied to the velocity gradient or shear rate. But you can see here the first derivative of the velocity is with respect to the radius of the tube, because we are dealing with, let's say, a pipe. All right, so then it should be expressed in terms of radius, or as long as it's cylindrical coordinate, depending on which coordinates that you are examining. And then this velocity gradient, it's to the power of the flow behavior index. So this gives us the power law relationship. So if we look at the K, the consistency index, it has the unit of Newton multiplied to the time, right, to the power of the flow behavior index per meter square. As for the flow behavior index, is a dimensionless number. and it depends on the type of fluid. So, for example, if it's Newtonian fluid, then we know that the N will be equals to 1. So when N equals to 1, the shear stress is proportional to the shear rate, and the K would then be the viscosity, right? The viscosity of the Newtonian fluid when N is equals to 1, which is Newtonian fluid. Then if it's N smaller than 1, it would be the pseudoplastic fluid. And if it's N, the flow behavior index of larger than 1, then it's the dilatant fluid, where the flow behavior, it will show us an increase in the viscosity with increasing shear rate. As you are introduced just now, we have Newtonian and non-Newtonian fluids. And then for non-Newtonian fluids, it can be further classified into time-independent and time-dependent non-Newtonian fluids. So time-independent Newtonian fluids is in which the shear stress is not dependent on the duration of shear. So it's time-independent. And we have examples like Bingham, the pseudoplastic fluids, and the dilatant fluids. As for time-dependent, so the shear stress is dependent on the duration of shear. And we have example, which is the thesotropic fluids and the rheopatic fluids. So if we look at the plot of shear stress as a function of shear rate, and if you examine for the thesotropic fluid, so you can see that these fluid, right, at constant shear rate. So let's say you draw a straight line here and at a constant shear rate, all right, you see that this fluid will exhibit a reversible decrease in the shear stress with time at constant fluid. So which mean at constant shear rate. So which mean at constant shear rate at earlier time, the shear stress is at this point. But as the time pass or proceed, then you see that the shear stress, it decreases. So it undergoes it exhibits a reversible decrease in shear stress with time at constant shear rate for thesotropic fluid. As for rheopatic fluid, if you observe here, so at constant shear rate, all right, at constant shear rate, the thesotropic fluid, it will exhibit a reversible increase in shear stress with time. So for example, at a constant shear rate, right? So let's say initially it's at a lower shear stress, but as time proceeds, the shear stress increases. So as compared to thesotropic fluid, rheopatic fluid are quite rare in occurrence. And if we look at thesotropic fluids, some of its examples are such as the polymer solution, shortening, or some food materials and paints. As for rheopatic fluid, examples would be like the bentonite clay suspension and the gypsum suspensions. So then let us further look at this plot here. So just now we mentioned the constant shear rate. So it might be a little bit difficult for you to visualize it with this plot here of shear stress as a function of shear rate. So let us plot this. If we plot the shear stress versus time for the time-dependent non-Newtonian fluid, so you can observe that at constant shear rate, so for the thesotropic fluid, right, you can see that the viscosity, it will decrease, right? Viscosity decreases as the time increase at constant shear rate. As for the rheopatic fluid, the viscosity increases as time increase. So to recap back on this section, so we know that fluid we can categorize into two types, which is the Newtonian and non-Newtonian fluids. So when we say Newtonian fluids, is the fluids that obey the Newton laws of viscosity, where the shear stress is proportional to the velocity gradient, and it has a flow behavior index n equals to 1. Then for non-Newtonian fluids, it can be categorized into two types, the time-independent and the time-dependent fluids. So which means the shear stress, it's not affected by the time. It's not a function of time for time-independent fluids, and we have example like Bingham plastic fluids where a yield stress is required to be applied on the fluid to initiate the flow. As for pseudoplastic fluids, so the flow behavior index is smaller than 1, and for dilated fluids, the flow behavior index N is larger than 1. Then next we have time-dependent fluids such as the thiotropic fluids where it will exhibit a reversible decrease in shear stress with time at constant shear rate, and the opposite would be the rheopatic fluids where it exhibits a reversible increase in shear stress with time at constant rate of shear. In the second last subtopic here, we are going to look into some dimensionless number. So example of dimensionless numbers are such as the Reynolds number, the Prandtl number, the Nusselt number, and the Biot number. So we may be using some of this dimensionless number when we analyze the flow behavior in this module. So let us look at the Reynolds number first. So a study have shown that the transition from laminar to turbulent flow in tubes is not only the function of the velocity, but it also affected by the density of the fluid and the viscosity of the fluid, as well as the tube diameter. So these variables are then combined into this equation here, which is known as the Reynolds number. And the Reynolds number is dimensionless. So for diameter, so as we know, this would be the diameter of the tube. It then has the unit of meter. As for the velocity, the average velocity of fluid, SI unit is meter per second. And fluid density, the rho, is in kilogram per meter cube. And as for the fluid viscosity, it's expressed as Pascal second for the unit. So for the Reynolds number, as you are introduced previously in many other modules, right? So the Reynolds number, based on the number, we can actually identify what type of flow we have, whether it's laminar, transition, or turbulent. So for the case of, let's say, we have flow of fluid in a straight circular pipe. So when the Reynolds numbers is less than 2100, then the flow is always laminar. And when the flow, right, the value of the Reynolds number is higher than 4000, then the flow will be turbulent. And in between, we call it as the transition region, where the flow, it can be viscous or turbulent, depending upon the apparatus details. So these are the Reynolds number for different types of flow regime in a circular pipe, straight circular pipe. Next, we have here the Prandtl number. So Prandtl number, you can see it in correlations that are used to determine the heat transfer coefficient or the mass transfer coefficient. So I believe you have applied this equation previously in your mass transfer module, where if it's in mass transfer, then the Prandtl number is defined as the ratio of the momentum diffusivity to the species diffusivity. So where you can see here, the Prandtl number is equals to the viscosity of the fluid divided by the product of the fluid density and the diameter of the tube or the channel. So now in this module, you might be using it to solve the heat transfer coefficient by determining what is the Prandtl number, then applying in a given correlation. Then we can use it to determine the heat transfer coefficient, like the H, the convective heat transfer coefficient. So then the Prandtl number in heat transfer, right, then it's defined as the ratio of the shear component of diffusivity for momentum to the diffusivity for heat. So if we look at the equation, so the Prandtl number, so at the top section here, so it's the shear component of the diffusivity for momentum, so which is the viscosity of the fluid divided by density, and then divided by this product. This here is the diffusivity for heat. So it's the specific heat capacity divided by density of fluid multiplied to the heat capacity. So if you simplify this equation, what we get is the Prandtl number will be equals to the product of viscosity and specific heat capacity divided by the thermal conductivity. So this is the equation for calculating the Prandtl number. Next is the Nusselt number. So Nusselt number, you have applied this equation here to do some calculation related to the mass transfer coefficient in the mass transfer module. So for now, we'll focus on what if we are using this dimensionless number in heat transfer study. So it's defined as the ratio of convective heat transfer to the conductive heat transfer. So it's generally used to calculate the heat transfer coefficient H. So if you look at here, so which means this H here is the convective heat transfer coefficient, the K, which is the thermal conductivity of the fluid, and D is the diameter of the flow in pipe. Or let's say if it's a plate, then this would be the length of the plate. So, and the last one here, we have the Biot number. So it's used in unsteady state fluid flow, and it's defined as the ratio of conductive to convective heat transfer resistance. So if you look at the equation, the Biot number is equals to the convective heat transfer coefficient multiplied to the, let's say if it's the length of the pipe or the length of the plate, so divided by the thermal conductivity of the solid. So if you're looking at the equation, you might find the equation for Biot number and the Nusselt number is quite similar. So the difference between them is the Nusselt number, it tells us whether the conductive or the convective heat transfer dominate across the fluid-solid interface. So it's across the fluid-solid interface. And as for the Biot number tells us whether significant thermal gradient will develop inside a solid by telling us the ratio of the heat transfer away from the surface of a solid to the heat transfer within the solid. So you can see here it says that we can use it to determine the uniformity of temperature in the solid. So that's the difference between the Nusselt and the Biot number. So for all the dimensionless number that we have covered here, like the Reynolds number, the Nusselt number, Biot number, Prandtl number, for the equation, do not worry. So it will be provided during the assessment or the final exam. Finally, we have come to the last section of Lecture 2, and this is the most challenging section as well in Lecture 2, which is about the shear stress of power law fluids flowing in pipe. So let's look at this equation here. The shear stress at the wall of a tube, it can be represented by this equation where you can see it's the tau W, which means shear stress at the wall of tube is equals to K prime multiplied to this terms here, which is 8V divided by diameter. So this is the average velocity, this is the diameter of tube, and this whole thing here to the power of the flow behavior index N prime. So if you look at this equation, it's actually just another statement, another form of the power law equation that you are introduced in earlier section when we talk about the non-Newtonian fluids, the power law equation, where it's the shear stress equals to the consistency index, right, multiplied to the negative velocity gradient to the power of n. Alright, so this is just another form of the power law equation. And why do we have this another form of power law equation? Because it's more convenient to use this equation for pipe flow situation, especially for flow in round tubes, like pipes, cylindrical duct. Okay, so now when the flow properties are constant over a range of shear stresses, then this K prime here is the derived consistency index, and it has the unit of Newton as to the power of m prime divided by m squared. So this derived consistency index is equals to K multiplied to this whole term here to the power of m prime. And then the n prime is the derived flow behavior index of n. So it's equals to the flow behavior index. And you can see here, so similarly, if it's a non-Newtonian, if it's a Newtonian fluid, the M prime will be equals to 1. So for pseudoplastic and Bingham plastic fluid, the M prime value would be smaller than 1. As for dilatant fluid, then the M prime value would be larger than 1. So this is another form of the power law equation that is used to calculate the shear stress at the wall of a cylindrical tube, or we call it the round tubes. So if you look at the term, the shear stress at the wall, so if you expand it, it can be expressed as these terms here, which is the diameter of the straight tube multiplied to the pressure drop. So you can see here the pressure drop in a straight tube, and then divided by 4 multiplied to the length of tube. So this whole term here, it represents the shear stress at the wall of the round tube, and it's equals to this equation that we discussed just now. As for the shear rate at the wall, so you can see here it negative first derivative of velocity with respect to the radius because it's in a round tube. So the shear rate at the wall for a round tube, so it's equals to this one here. We have 3n prime plus 1 divided by 4n prime multiplied to 8 multiplied to, this is the average velocity of the fluid divided by the diameter of the straight tube. And next here we have table 3.51, where it shows most of the typical flow property constant for some fluids. So here in this table you can see some of the different kinds of fluids, and then the flow behavior index in M prime, and then this is not shear rate, it's called the generalized viscosity coefficient. So you can see in this table here, for some fluids, the generalized viscosity coefficient is given instead of the flow behavior in this one, the consistency index, the K. So let's say if you like to find out what is the K value, the consistency index, then it would be, you can use this equation here where the generalized viscosity coefficient is equals to K prime multiplied to 8 to the power of n prime minus 1. So you can rearrange it so that you can find out what is the value of the K prime. Next, we are going to look at the methods that are used to predict the frictional pressure drop. And think that the methods that we are going to discuss, it's applied to fluid flow in round tubes and in laminar manner. So for laminar flow only in round tubes. So there are two methods, one which we call it the power law method, and another one is the friction factor method. So as the name implies here, so the first method is related to the use of the power law equation. So if you look at this equation here, it's actually derived from this power law equation for shear stress at the wall. So if you rearrange this equation, then we can have the pressure drop expressed in terms of this multiplied to 4L divided by the diameter. And this is what we get. So now, as this equation only applies, it will be only proper to apply for laminar flow. So when you use it to slow the pressure drop, we have to also do one more step here, also calculate the Reynolds number to make sure that it's a laminar flow. So if it's a laminar flow, then for flow in round tubes, in pipes, the Reynolds number should be smaller than 2100. Then the next method is the friction factor method. So the friction factor method, then we will use this equation here where the pressure drop is equals to 4 multiplied to the friction factor multiplied to the density of the fluid and multiplied to the ratio of the length of the tube to the diameter of the tube, and V squared divided by 2. So we are going to use this equation if it's for friction factor method. So Now, then how do we find out what is the friction factor value? So it can be determined by two methods. One is by using this equation, another which is by using figure 3.53. So this will be explained later. So if it's by equation, then the friction factor is equals to 16 divided by the generalized Reynolds number. So if we are using friction factor method, then the generalized Reynolds number, this equation has to be used, especially when we are dealing with non-Newtonian fluids. So you can see here, for non-Newtonian fluids, the generalized Reynolds number is used in the calculation to determine the fanning friction factor, which is this equation. So we should not be using the Reynolds number equals to rho Vd per mu when we are showing the friction factor value for non-Newtonian fluids. So in this lecture, I've included one example here on how to apply the two different methods to solve the pressure drop in straight tube for fluid which is in laminar flow. So you can go through this, or you can follow me here where I'll just brief you through quickly. So for example, if we have a power law fluid having a density of 1041 kg per meter cube, flowing through a 14.9 meter of a tubing, so which means it's a circular or round tube having an inside diameter of 0.0524 meter at an average velocity of 0.0728 meter per second. So you are given also the rheological or the flow properties of the fluid, which are K prime is equals to 15.23 Newton second to the power of n prime per meter square, and you're given the n prime is 0.4. So you can see here the n prime value is smaller than 1, which means if it's smaller than 1, it could be a pseudoplastic or Bingham plastic fluid, but it did not mention here, so you can just assume. Alright, so then here the instruction is you need to calculate the pressure drop and the friction loss using the equation below for laminar flow. And at the same time, because you are using this equation, which is the method number 1 that we discussed just now, which is the power law model, and for applying this equation, we'll need to make sure also that it's in a laminar flow region, because if you look at the question, it's not mentioned whether it's in laminar flow or not. So you need to check the generalized Reynolds number to make sure that the flow is laminar. And then you're given this equation here, the power law model equation for the pressure drop. So we are supposed to calculate the pressure drop and also the friction loss. This is for part 1. And for part 2, we'll need to repeat calculating the pressure drop but using the friction factor method. Okay, so you can either pause here if you want to try this example, or it will just you can also follow me and we'll go through the solution. So now the first method, which we are supposed to solve using the power law model equation, so which is given by the delta P and equals to here. So from the question just now, we are provided with K prime, the length of the tube, the diameter of the tube, and the average velocity and the n prime value. So we'll just need to substitute everything, alright? So, and then equating the units and cancelling out, you find that the pressure drop is equals to 45,390 Newton per meter square. So this is the pressure drop for the power law fluid that is flowing in a straight tube with a diameter of 0.0524 meter and a length of 14.9, which is at this average velocity, and for power law fluid with this density and these rheological properties. Okay, so then besides the pressure drop, the question also requires us to calculate what is the friction loss. So friction loss is equals to the pressure drop divided by the density of fluid. So it's equals to 43.60 joule per kg. And remember, when we are applying the power law equation to solve for the pressure drop in straight tubes with fluid in laminar flow, we'll need this because this only applies to laminar flow, this equation. So you need to check the Reynolds number. So applying the generalized Reynolds number equation, so you can substitute all the data that we have in the question. Okay, so then these would be equals to 1.106. So it's smaller than 2100, so it's a laminar flow. The flow is laminar. And then when it comes to part B, where we are supposed to solve it using the friction factor method. So for the friction factor method, we'll need to first find out what is the friction factor value. So you can either use the figure 3.53 or we can use this equation here, which is 16 divided by the generalized Reynolds number, which you have solved just now here, 1.106. So the friction factor is 14.44. Okay, so substituting it into the equation for pressure drop, which is in terms of expressed as a function of the friction factor. So substituting all the L, the length, the diameter, velocity, and the density of fluid. So solving this, the pressure drop is equals to 45.39 kilonewton per meter square. So you can see here the answer is very close. It's actually exactly similar to the answer that we get from the method where we solve using the power law model. So just now are the examples and methods that are discussed for how to determine the pressure drop in round tubes for fluids that is in laminar flow. So we know that fluids can flow in laminar flow or in a transition region or in turbulent flow. So how do we determine the pressure drop in round tubes for turbulent flow? So if it's for turbulent flow, we can still apply the friction factor method by calculating the pressure drop using this equation. But take note that if it's the turbulent flow, so when we determine the friction factor, we can no longer use this equation. For turbulent flow, we cannot use this equation. So we have to use figure 3.53, which is this one, to determine what is the friction factor value. So if you look at these figure 3.53, so the curves for different M prime values, so different types of fluid, we have Newtonian when the M prime is 1 or larger than 1 and smaller than 1, which is for non-Newtonian fluid. So the curve for different M prime values, they break off from this laminar line. So this is the laminar line at different Reynolds number to enter the transition region. So you can see this is a plot of the friction factor as a function of the generalized Reynolds number. So if you calculate the Reynolds number in straight tube when it's smaller than 2100, so you can see here smaller than 2100, so these are the friction factor for different Reynolds number smaller than 2100 in laminar flow. So as for example, you can see here when the M prime value is equals to 1 for Newtonian fluid. Alright, so you can look at here for Newtonian fluids. So this transition region start as this generalized Reynolds number equals to 2100. And here, since most of the non-Newtonian power law fluids, they have very high viscosity, so they are often flowing in laminar flow. And another point here is that the correlation for a smooth tube is also hold for a rough pipe in laminar flow. So what does this mean? So it's stated here, in other words, which mean that the pressure drop in fluid with laminar flow is unaffected by the roughness of the tube, because sometimes the inner surface of the pipe, it could be smooth, it could be a smooth pipe, or it could be a rough pipe. So here we have an enlarged picture of figure 3.53 so that it's easier for you to use it for determining the friction factor at different flow behavior index and generalized Reynolds number. And here, so continue from the previous slide. So these would be used, this figure would be used to determine the friction factor for turbulent flow in smooth pipe. So take note here, you can see it's written here in smooth pipe. So let's say if it's a rough pipe, so the rough pipes, it has various values of roughness ratio, and therefore these figure will not be suitable to use to determine the friction factor because it does not account in the roughness of the pipe. Okay, instead the estimation of the friction factor value, it needs to be estimated from these figure here, figure 2.103, where you can see that it's a plot of the friction factor at different Reynolds number, and also taking into consideration for different roughness ratio for the tubes. So you can see here for different types of tubes there's different roughness. So the relatively roughness ratio is actually you can see here the epsilon value, which is the equivalent roughness for a new pipe divided by the diameter of the pipe. So with this value, so you determine at which roughness ratio, and then you need to find out what is the generalized Reynolds number, then you can determine what is the F value. And you can see here the last curve here is for if it's a smooth pipe, and you can see if it's a laminar flow, all right, if it's laminar flow and in smooth pipe, then the friction factor value, it will drops under this region here, this straight line here. Now let us look at the last example of this lecture 2. So we have here example 3.52, and this example is from the Jean Copley's book. So we have, let's say, a pseudoplastic fluid that follows the power law, and it has a density of 961 kg per meter cube. It is flowing through a smooth circular tube having an inside diameter of 0.0508 meter at an average velocity of 6.1 meter per second. And you are given that the flow properties of this pseudoplastic fluid are m prime equals to 0.3 and k prime equals to 2.744 Newton second to the power of n prime per meter square. So you need to calculate the frictional pressure drop for tubing of 30.5 meter long. So now we know there are two methods to calculate the pressure drop, but it depends also on whether it's laminar and turbulent flow. So and it's also affected by whether the pipe is a smooth pipe or a rough pipe. So for this example here, it's clear that we are dealing with a smooth pipe because it says that it's flowing through a smooth circular tube, and we are dealing with round tube. But to decide which method to use, whether it's the power law model or the friction factor method, then it has to depends on whether it's laminar or turbulent flow. So that's why the first step, then we should first find out what is the generalized Reynolds number. So now with the data given, the K prime, the diameter, the average velocity, density, and the length of the tubes, so apply the generalized Reynolds number equation first, solve it, and you see that it's equals to 1.328 10 to the power of 4. So if you recall back, for flow in round or circular straight tubes, so if the Reynolds number is higher than 4000, which means it's in a turbulent flow region already. So this flow is turbulent. So if the flow is turbulent, which means the power law model equation is not suitable to be applied in this case. Instead, we'll need to apply the friction factor method. And for the friction factor method, if you recall back, right, to find this is the equation where we use to solve the pressure drop using the friction factor method. And for the finding the friction factor value, so we have two methods, right? So it's either equals to 16 divided by general generalized Reynolds number or by using the figure. But since this is a turbulent flow, which means we can't use F equals to 16 divided by generalized Reynolds number. Instead, for finding this F value, we need to use figure 3.53. So if you check figure 3.53, so we are given that the flow behavior index, the M prime, is equals to 0.3. So we will need to look along this curve here, and we are given also that the generalized Reynolds number is equals to 1.328, 10 to the power of 4. So which means it will be somewhere here, right? So the intersection would be somewhere here, 1.328, 10 to the power of 4 for the generalized Reynolds number. And then at M prime equals to 0.3, and if you trace it, so you can see that the friction factor would be around 0.0032. Okay, so you can find the fanning friction factor by using figure 3.53 because this is for turbulent flow. We are dealing with turbulent flow in round tubes. Then substituting it into this equation, so you can see here 0.032, alright. Then substituting the density, the length of the tube, the diameter, and the velocity. So the pressure drop is equals to 137.4 kilonewton per meter square. So this is how we solve for the pressure drop in straight tube for fluid in turbulent flow. So that's all for this lecture 2. In the tutorial session, we are going to discuss with more examples. And yep, that's all for our lecture 2, the recorded pre-recorded lecture video. And thank you very much for watching.